spent a session learning some basics of capacitors, what the whole idea is, and some basic arrangements that could act as storage of charge, storage of electrical energy, energy implications associated with it, some very basic computation tagged onto it. So let's learn a few more things as an addendum to what we did in the previous session on capacitors. I'm assuming that all of you have bred familiarity and comfort level with things that have been done in the previous session, right? Now, by and large, we'll deal with parallel plate capacitors. We will look at now collection of capacitors arranged in various ways, right? Say there are these three capacitors. Capacitances C1, C2, C3. Connected between points A and B. There are these three capacitors C1, C2, C3 connected between 2 points A and B. I want to be able to replace this set of three capacitors, this arrangement of three capacitors, with a single capacitor. And that would be referred to as the equivalent capacitance of this arrangement between points A and B. Right. Now, the moment somebody says, find the capacitance of this arrangement between 2 points A and B, you must understand what this means. Find the capacitance of the arrangement between A and B. What it really means is, no matter how complicated a network is between A and B, you know, there could be a maze of capacitors connected in various ways. It could be intricate. But what is fundamentally meant by capacitance between points A and B? It means that you mentally imagine a battery to be connected between these 2 points. Mentally imagine a battery to be connected between 2 points. Find the capacitance between A and B means mentally imagine a battery to be connected between these 2 points. Say there is this battery of EMF V volts. Does not matter how you put the polarity in perspective. And now once you connect a battery between these 2 points, the battery would act as a conduit of charge. There would be flow of charge across the terminals of the battery, right? And until such time that steady state conditions have been attained, right? So I imagine a battery of EMF V volts, which results in charge Q flowing through the battery, till the point of acquisition of steady state, Then the capacitance between these 2 points A and B, is defined as the charge flowing through the battery divided by the potential difference, the EMF that the battery maintains, Q divided by V is the equivalent capacitance between A and B, is the equivalent capacitance between points A and B. This is what is meant by equivalent capacitance. Now, which means essentially what it means is, if this is the equivalent capacitance between points A and B, then for a battery of EMF V connected across this and a battery of EMF V connected across this, the same charge will flow. The same charge will flow through the battery. This is what it means. That's when the two arrangements are referred to as equivalent, right? For an identical battery connected between points A and B, you must have the same amount of charge flowing through the battery. Switch that off. Now, suppose a charge Q flows through the battery in this arrangement. And we will assume that the three capacitors were uncharged initially. The three capacitors were uncharged initially. Look at this plate. It is this plate which would have lost charge Q. It would now have a charge minus Q on its inner surface. Charge minus Q here. It all means on the inner surface, because I don't have enough space in the inside. I write it here, but it all means on the inner surface. Now this Q goes there and it accumulates here. It accumulates here, right? Now once it accumulates here, it would induce charge minus Q on this plate. It would induce charge minus Q on this plate. Now, these two plates are electrically talking to each other, right? They can exchange charge. Together they were electrically neutral. Now if a minus Q appears here, it must be because there is a plus Q there to maintain electrical neutrality between these two plates, right? These two plates will only exchange charge with each other because they are physically connected. This plate can't exchange charge with this plate, or this plate can't directly talk to this plate in terms of exchange of charge. Now, meaning therefore that this plate has charge Q, again inducing charge minus Q on this plate. These two are electrically neutral, leaving this with charge plus Q and minus Q, right? And again, if Q leaves this, then this plate has charge minus Q, this plate has charge plus Q. Yes or no? Now, equivalence means the total drop from A to B here is V volts. That must be the same as the total drop from A to B there. This is what it means. The total drop from A to B here must be the same as the total drop from A to B there. That's when these two arrangements are looked upon as equivalent arrangements. Clear? Now, the drop, see, if there is a capacitor, one thing that you must remember, if there is any capacitor, this plate has charge Q, this plate has charge minus Q, and this has capacitance C. And let's say this plate is P1 and this plate is P2. Now if you go from one plate to another, P1 to P2 for example, if you go from one plate to another, say P1 to P2 for example, then the potential drop from one plate to another, plate 1 to plate 2, would be algebraic potential drop. The algebraic potential drop, delta V, from P1 to P2, from one plate to another, is going to be charge on the first plate divided by C. Charge on the first plate divided by C. Charge on the algebraic charge on the first plate, Q divided by C. That's the potential drop when you go from P1 to P2. That's the algebraic potential drop, mind you. That's the algebraic potential drop from P1 to P2. Charge on the first plate divided by C. If you go from P2 to P1, then the drop in this direction would be charge on the first plate, which is minus Q divided by C. Adhere to this convention, adhere to this notion, right? If you go from one plate to another, then the algebraic potential drop is going to be algebraic charge on the first plate divided by C. That's going to be the algebraic drop, right? Now, so when I go from A to B, the total drop that I would encounter is V volts, right? Why? Because see, this plate is connected to this point is connected to this terminal of the battery, and therefore these two are electrically identical. This plate terminal is connected to this point, and therefore they are electrically identical. So the drop here is the same as drop from A to B, because this and A are electrically identical, this and B are electrically identical, right? Now the drop from here to here across the first plate is Q by C1. When I go from here to here, Q by C1. then the drop from here to here is going to be Q by C2. Drop from here to here is Q by C3. This then must be the same as the drop from here to here, which is Q by C equivalent. That means the equivalent capacitance of this arrangement is given by 1 by C equivalent as 1 by C1 plus 1 by C2 plus 1 by C3. That's the equivalent capacitance of this arrangement. And between A and B, these three capacitors are said to be capacitors in series. These capacitors are said to be capacitors in series. So capacitors in series are like resistors in parallel. Capacitors in series behave like resistors in parallel. Can I wipe this off? Similarly, we could have had an arrangement of the following kind between 2 points. Say between points A and B, I have an arrangement of two capacitors C1 and C2 connected as shown. Now, I want to replace this arrangement with one single capacitors between points A and B. That's the C equivalent. Which means I would imagine a battery of V volts to be connected between A and B here, which results in a flow of charge Q. And if the same battery is connected here between points A and B, it will result in flow of charge Q as well. That's when the two arrangements are looked upon as being equivalent between points A and B. Okay. Now, realize that if a charge Q flows through this, part of this charge must have come from here, part of this charge must have come from there. That means this loses, let's say, Q1 units of charge, leaving this with minus Q1, and say this loses Q2 units of charge, leaving this with minus Q2. Right? That means Q must be actually Q1 plus Q2. So charge Q comes to A and it gets distributed into Q1 here and Q2 there, where Q1 deposits on this and Q2 deposits on this. Now, the drop here is what? Q1 by C1. Between, when I go from this plate to this plate, the drop is Q1 by C1. That's also the potential difference between A and B, because this plate is electrically the same as A and this plate is electrically the same as B. So the potential difference between A and B is V volts, and that's also the potential difference across C1, right? So then the drop across C1 is Q1 by C1. The drop across Q2 is Q2 by C2. Right? Yes or no? And that must be the same as the drop across the C equivalent, which is Q by C equivalent. When I go from here to here, the charge arrangement in this is minus q and plus q. So realize that the drop across this capacitance is the same as drop across this capacitance, because both capacitors are connected to the same 2 points electrically, A and B. Yes or no? You know what I'm saying? So each of these then must be equal to the drop across C equivalent, which is Q by C equivalent. Yes or no? Equal to V volts, equal to V volts. Very clearly then. If this is equal to this, then each will be sum of the numerators divided by sum of the denominators. So each of these then is equal to sum of the numerators, which is Q1 plus Q2, divided by sum of the denominators, which is C1 plus C2. Q1 plus Q2 is Q. So this is Q by C1 plus C2. So C1 plus C2 must be C equivalent. So the C equivalent of this arrangement between points A and B is C1 plus C2, and this kind of an arrangement is called capacitors in parallel. This is called C1 and C2 are said to be in parallel across AB. And capacitors capacitors in parallel are like resistors in series. Capacitors in parallel behave like resistors in series. Clear? Now, all's good, right? We could have had several arrangements in which you could have had capacitors in series, capacitors in parallel, combination of the two, or neither in series nor in parallel. But there is a general principle that we are going to understand and deploy all the time. In any electrical circuit containing a number of electrical elements, it could be capacitors, it could be resistors, combination, some batteries, and so on and so forth. Say there could be some electrical elements. This is an electrical element, this is another electrical element, and say there is a battery here of EMF epsilon 1, and there is a battery here of EMF epsilon 2 with polarities connected as shown. And these could be any two electrical elements. These could be any two electrical elements. These could be resistors, these could be capacitors, does not matter. The rule of the game is that if the drop here is V1 volts, the drop across this element is V1 volts, algebraic drop. The algebraic drop across this element is V2 volts. Right? And you traverse this loop in a certain manner. You traverse this loop in a certain manner. Then the algebraic sum of the potential drops must be 0. The algebraic sum of the potential drops in any closed loop must be necessarily 0. So that means this is an algebraic drop here, V1, it could be positive or negative. This is the drop here, the drop, V2. Then when I go from here to here, there is a drop of epsilon 2, so plus epsilon 2. When I go from here to here, there is an increase of epsilon 1, that means a drop of minus epsilon 1, that means a drop of minus epsilon 1. Minus epsilon 1 must be 0. The algebraic sum of the potential drops in any closed loop must necessarily be 0. This essentially is what is referred to as KVL or Kirchhoff's voltage law. This is actually Kirchhoff's voltage law. Or KVL. So this we would apply to all kinds of circuits. at any given instant of time, be it steady state conditions or non-steady state conditions at a given instant of time. This V1 and V2 could be functions of time, does not matter. But the algebraic sum of the drops in a closed loop must necessarily be 0. That's Kirchhoff's voltage law. Now this gives us an opportunity to understand what happens in an electrical circuit, in which there is a capacitance, there is a resistance, there is, you don't have to imagine a resistance. The wires that connect would have their own resistance. So it's not like there has to be a resistance element in the circuit. And one thing that we will of course understand it better in current electricity when we do that. But if there is a resistance R and current flows from A to B, then in the direction of the current, potential will drop. The potential drops in the direction of the current by an amount I into R is the potential drop. A is positive compared to B. That means A would be at a higher potential compared to B. If you traverse in the direction of the current across a resistance, then the algebraic potential drop would be I into R. That's the algebraic potential drop in a resistance. See, if there is a capacitance C and a resistance R and a battery of EMF epsilon, say this is a switch, I have an initially uncharged capacitor and I want to charge it to capacity in this circuit. What happens is, initially, like I told you in my first class, positive charges would be drawn out of this, so that this becomes negatively charged and its potential comes closer and closer to the potential of this terminal of the battery, and that positive charge would move across the terminals from negative to positive terminal and would deposit on this, attempting to bring the potential of this terminal equal to this terminal. Eventually, what happens is, the potential of this becomes equal to the potential of this, the potential of this becomes equal to the potential of this, the drop here becomes equal to the drop there. Once the potential of this and this get equalized, potential of this and this gets equalized, that means the drop here across the plates of the capacitor becomes equal to epsilon. There would be no further, beyond this point, there would be no further charge communicated through the battery. Once that happens, we say steady state conditions have been attained. But until then, that means there is flow of charge, across this, in this loop, and once steady state is obtained, once steady state is acquired, there would be no further flow of charge from one plate to another, and the current in the circuit will reduce to 0. This process is called charging of the capacitor. Now, how does the capacitor get charged? So, by and by, more and more negative charge will accumulate on this, more and more positive charge will accumulate on this, right? So the charge that accumulates on the plates of the capacitor is a function of time. Let me look at the regime before the capacitor acquires steady state. Well, before the capacitor acquires steady state, let's see how charge varies with time. Let's examine how charge on the plates of the capacitor, an initially uncharged capacitor, will vary with time. That is what we would examine. So at t equal to 0, there was no charge on the plates of the capacitor. I At t equal to 0, I activated this switch. Once I activate this switch, there would be flow of charge across the battery. A current will get initiated in the loop. A current will get initiated in the loop. This current will be a function of time. These conditions, when things depend on time, the charge on the plates of the capacitor, the current in the circuit depends on time, we call these conditions transient conditions. We call this transient conditions. As opposed to steady state conditions. Steady state conditions, things don't change once steady state is acquired, right? But in transient, so let me look at this transient state. Let me look at this transient state. So after t equal to 0, let's say at an instant of time t, this would have lost until then a charge q, which would have deposited on this plate. This is an instantaneous situation of the circuit. And at this instant of time, let's say there is a current I. There is a current I that flows in the loop at this instant of time t. Now this I will be a measure of the rate at which this charge accumulates on this plate. Will be a measure of the rate at which this charge accumulates on this plate, yes or no? I would actually be measured by dq dt in this case. In a more general sense, mod of dq dt would measure the current. Rate at which this charge changes with time, rate at which this charge changes with time will be a measure of the current flowing in the circuit. Now, in this case, you realize this q is increasing with time. This q is increasing with time. So if q is increasing with time, dq dt is positive. Remember the class yesterday, increasing decreasing functions? dq dt is increasing with time. And if dq dt is q is increasing with time, so dq dt is positive. And if dq dt is positive, mod of dq dt would be simply dq dt. Mod of dq dt would simply be dq dt. Isn't it? Because the quantity inside is positive. Now, for this instant, let me apply KVL in the loop. Let me apply KVL in the loop. Algebraic sum of the potential drops must be 0 for this instant of time. Now, when I go from here to here, what's the drop? Q by C. Charge on the first plate divided by capacitance, that's the drop. When I go across the resistance, the drop across the resistance will always be I into R, the algebraic drop. When I go from here to here, the drop is minus epsa, because there is an increase. I'm traversing the loop like this, right? So minus epsa, that must be 0. Yes or no? Does it make sense? Right? Now solving this would enable me obtain charge that deposits on the plate of the capacitor as a function of time. Charge that deposits on the plates of the capacitor as a function of time, right? This I can write as, do you understand all of this? How I applied KV, I can explain again if there is an issue. Clear? So I have, this is KVL applied to this loop. The drop from here to here is Q by C. The drop here is IR. Here to here, the drop is minus epsa. The algebraic sum of the drops in a closed loop must be 0. Now, this I write as dq dt, right? So I end up getting R dq dt plus Q by C must be equal to epsa, right? Or R dq dt, R dq by epsa minus Q by C is dt. R dq by epsa minus Q by C is dt. Do you realize what I did? I transposed this on this side and then brought it in the denominator, and d2 I brought there, right? isn't it? And now I integrate both sides. I integrate both sides. At t equal to 0, the charge was 0. At t equal to t, let's say the charge becomes q. The charge becomes q. This will give me q as a function of time. This would give me q as a function of time. Now what I could do is, this will become C epsa. This will be RC. What's the derivative of the denominator with respect to q? -1. If I multiply with a minus, then I can make the numerator the derivative of the denominator, right? Minus, to balance this minus. Now the numerator is the derivative of the denominator. Integral will be log mod denominator. Yes or no? So the integral becomes log of C epsa minus q. Numerator derivative of denominator. Recall this? Integration? Huh? No? Okay. Even if you had cared to, watch the first session that I have uploaded on YouTube, you would have known this. I have done this way back in class as well. So, numerator becoming the derivative of the denominator, integral would be log of the denominator. Q runs from 0 to q. That must be minus t by RC. That must be minus t by RC. This will give me transient variation of charge with time, which is log of C epsa minus q divided by C epsa when I supply the limits, isn't it? At q, it's log of C epsa minus q. At q equal to 0, it's C epsa. So log a minus log b, log a by b, right? And that must be equal to minus t by RC. Right? This would give me cross multiply q equal to C epsa into 1 minus e to power minus t by RC is what I get. Q equal to C epsa into 1 minus e to power minus t by RC is what I end up getting. Bless you. Q tends to CE. This is how Q varies with time. This is how Q varies with time. Right? Now, T tends to infinity very clearly. This will tend to 0. So the charge tends to C epsa, which is the steady state charge on the plates of the capacitor, which is the steady state charge. Now, see, you might be tempted to believe T equal to, that means if you have to charge a capacitor to steady state conditions, you will have to wait for infinite amount of time. This is what it might tempt you to believe. To charge a capacitor to steady state, that means if you start today, your great grandchildren will see steady state, or their great grandchildren will see something like steady state. No. Now, when I say T equal to infinity, see, what it really means is, see, R is of the order of, say, a few kilo ohms. C is of the order of, say, few microfarads, right? So RC is actually a very small number. First of all, the unit of RC must be time. Do you realize that? Because this has to be dimensionally. So RC has units of time. So RC would be like a few nanoseconds. RC could be like a few nanoseconds. And if RC is few nanoseconds, then T, a few microseconds, is like infinite compared to nanoseconds. It'll be like 1,000 times nanoseconds, right? So which means even if you instill the circuit for a few nanoseconds or few microseconds, then those microseconds would be large compared to RC, and then T by RC will be a very large number. That means T will be very large. For all practical purposes, a few microseconds will behave like infinite time. And in those few microseconds, you would have acquisition of steady state. Steady state conditions would be practically acquired. Right? So, this is transient charging characteristics of the of an uncharged capacitor. Now, once steady state conditions are acquired, there would be no further charge exchange. Right? This is the steady state charge. Ceps are here and minus Ceps are there. And then there would be no flow of current. That means the current in this loop becomes zero under steady state conditions. Which means, if you really think of it, this capacitor behaves like a monster under steady state conditions. It offers infinite resistance to the circuit. If there is infinite resistance in the circuit, the current flowing through the circuit would be practically zero. So under steady state conditions, if there is a branch of a circuit that contains a capacitor, under steady state conditions, if there is a certain branch of a complicated circuit containing a capacitor, then in that branch there would be no current flowing, because the capacitor element under steady state conditions behaves like an infinite resistance. Theoretically, it behaves like an infinite resistance, preventing flow of current. Now, let me draw this charge as a function of time. Charge grows from 0 to a maximum, C epsilon. Charge grows from 0 to a maximum, C epsilon. This is how it happens. At t equal to 0, charge was 0. But dq dt was not 0. Therefore, charge was growing. Q was growing, right? If you differentiate this, then at t equal to 0, dq dt is not 0. See, what is dq dt at any given instant of time? That's the current. dq dt at any given instant of time will be the current, right? This is C epsa into by RC e power minus t by RC when you differentiate this, which is epsa by R e power minus t by RC. That's a current at any given instant of time in the circuit, right? Now notice one fact. At t equal to 0, current I0 was epsa by R. Yes or no? If the current was epsa by R, it was as if this circuit had only a resistance. That means the capacitor element behaved like zero resistance. An uncharged capacitor behaves like zero resistance. Under steady state conditions, a capacitor will behave like infinite resistance in the circuit, right? Also, do you realize that current is decreasing? While charge is growing, current is decreasing as time is increasing, isn't it? As t increases, e power minus t by RC will decrease. So while charge increases, current decreases. Yes or no? So while Q grows, the rate at which it is growing will decrease. The rate at which it's growing, dq dt is the rate at which current is growing. That's a rate at which charge is growing, that will decrease. So while charge increases, current progressively decreases exponentially. Now, eventually, charge attains what is called a steady state value of C epsa, a steady state value of C epsa. And Notice, at any given instant of time t, the current would be given by dq dt. dq dt is what? The slope. The slope of this tangent at this instant of time will be dq dt, the current. Do you realize? And as you go further and further, the slope of the tangents will decrease. If the slope decreases, means current is decreasing. Yes or no? So dq dt is decreasing. dq dt is decreasing. That means dq dt is a decreasing function of time. That means derivative of dq dt must be negative. Derivative of dq dt is negative, isn't it? If dq dt is what? The slope of the curve. And if the slope decreases, that means dq dt is decreasing. When dq dt is itself a function of time. If dq dt decreases, that means its derivative must be negative. That means what is the derivative of dq dt? d2q dt2. That's the derivative of dq dt. That must be negative. That must be negative. Yes or no? Do you all understand this? Huh? All's good? The current as a function of time. This is current as a function of time. This is how current behaves. At t equal to 0, it's epsilon by r. At t equal to infinity, the current becomes 0. At t equal to infinity, current becomes 0. Now, see, q versus time. This is the growth of charge. This is the growth of charge in the capacitor. And the steady state charges C epsilon. The steady state charges C epsilon. Clear? Now, at an instant of time t equal to RC, what is the charge? See, RC must have units of time. Do you realize that? T by RC must be dimensionless. RC must have units of time. So, resistance into capacitance is actually like time. So, at an instant of time t naught equal to RC, what is the charge? What is the charge at t equal to RC? Put t equal to RC. This will become 1 by E. 1 by E is roughly 0.37. 1 by E is roughly 0.37. So 1 minus 0.37, that is roughly 0.63. So this will become 0.63 times RC. This will become 0.63 times RC. That means in time equal to 1 RC, in a time equal to 1 RC, which is like a few nanoseconds, for example, the charge, I'm sorry, C epsilon. The charge on the plates of the capacitor would have reached 63% of steady state charge. C epsilon is the steady state charge. That means in a few nanoseconds, the charge has already acquired 63% of steady state. Do you realize that? In a time equal to 1 RC, in a time equal to 1 RC, 63% of steady state has already been acquired, attained, right? This RC therefore measures the rapidity with which steady state would be attained, right? If RC is small, then steady state is acquired faster. If RC is more, it will take longer for steady state conditions to be attained. This RC therefore is an important number for electrical designers. For designers of electrical circuits that contain resistance and capacitance, this RC then becomes of monumental importance. And based on this, so this value of RC will be an indication as to how quickly steady state can be attained in that circuit, right? This RC then is an important factor and is called the time constant of the circuit. Tau is referred to as tau, the time constant of the circuit, electrical circuit. of the RC circuit. This is called an RC circuit. Got me? So in a time equal to 1 RC, 0.63 times steady state charge has already been acquired. These are the charging characteristics of an uncharged capacitor connected to a battery, right? Now, can I wipe this off? There are times you want to discharge a capacitor. There are times you want to discharge a capacitor. How does one discharge a capacitor? Suppose you have charged a capacitor to a certain degree and you want to discharge the capacitor. Yes, yes. I'll tell you how. Huh? Sorry? Nahin. If you remove the battery, no. I must explain this to you. I'm glad you made such a bizarre statement, but it'll help you understand the idea. See, if I have charged a capacitor, with the aid of this battery, V volts, huh? And there is a switch here. Suddenly you open the switch. How will it get discharged? Where will the charge go, dude?
I said remove the battery from the circuit. Keep the circuit on.
Remove the battery, which is like removing the switch.
Sir, he's saying remove the battery and connect the wire.
Which is dangerous.
But you didn't mention it shouldn't be dangerous.
No. No, it's all right, you know. We can afford to be dangerous. So if this has zero resistance, and you know, you could have done this also. You could be even more dangerous. Connect the two plates like this. There'll be flow of charge. There would be a spark generated, heat, light and sound. It'll burn the plates, it'll burn this system, it'll burn your heart. All right. You can discharge. That's one way to discharge. But you don't want to do anything abruptly, right? When you apply a brake, you don't want the car to stop at the instant when you apply the brake. If that happens, it brings back old fond memories. Long time. Now, so you don't want to do that, you know? Just like you don't want the car to stop at the instant you apply the brakes, the car will topple. If the car were to stop at the instant you apply the brakes, the car will topple. God knows what would happen to you inside the car. मर जाए तब तक तो ठीक है, अगर जिंदा बचा रहे उसके बाद तो मरने से बदतर होगा वो, नहीं? फिर भी ठीक है, कटा हुआ हाथ मतलब. Think of it, dude. The whole pleasure of life will go away. बड़ा होने दो इसको. राज बेटा तुम बहुत मार खाएगा किसी दिन, इसमें ताकत आ जाएगा ना, उस दिन ये सोच के रखा है, जिस दिन ये ताकत आ जाएगा इसमें तरह तरह का, the first person he'll fuck out of shape is you. है? कहाँ गया? कितने दुश्मन बना लेगा राज. हैं? तेरा लाइफ सबसे ज्यादा अनसेफ है, इसीलिए तुमको सेफ्टी का कोई चिंता है। तुमको तो पता है साला कोई ना कोई तुमको यहाँ पे इतना दुश्मन बना दिया, बाहर कितना होगा, स्कूल में कितना होगा, तुम्हारे कॉम्प्लेक्स में कितना होगा, पता नहीं। सोचो यहाँ 2 घंटे के पीरियड में तुम मतलब इतने लोगों से दुश्मनी मोल लिए हो ना कि अब तुम सेफ कहीं पर भी नहीं हो। और अभी तो ये पहली मंजिल है। हाँ बोल।
सेफ नहीं हो तो मजा क्या है? सेफ हो तो जिंदगी का मजा क्या है?
क्या बात है, क्या बात क्यों भैया, क्या बात है, ये तो मतलब सच अ फिलॉसफी ऑफ लाइफ। वाह वाह वाह, मजा आ गया सुन के, महाराज की बात सुन के। राजानंद जी महाराज हैं ये। अच्छा चलो, नाउ नाउ we don't want the capacitor to be charged abruptly. What is done? Discharged abruptly. Like it is not charged abruptly, it is not to be discharged abruptly also. We want the capacitor to lose its charge exponentially. This is what we really want. And in order to be able to do that, see, there is a capacitor here which is charged to the extent of Q naught. Capacitor charged to the extent of Q naught. And you want to discharge this. What you do is you connect the two plates through what's called the bypass resistance. This is a bypass resistance. This is a bypass resistance. You could have connected it through almost a zero resistance when things will happen abruptly and heavens will catch fire. Now what happens is that this is higher potential compared to this. So there would be flow of charge from this plate to this plate via the resistance. There would be a current generated progressively. There would be more and more heat generated in this resistance. The joule heating in this resistance would be at the expense of the electrical energy half CV squared between the plates of the capacitor. By and by, the capacitor will get discharged. Let's examine the discharging characteristics of this capacitor C, initially charged to Q naught. Right? So this is at time t equal to 0. This is the state of the circuit at time t equal to 0. T seconds later, this becomes Q, this becomes minus Q. This bypass resistance, which is consuming the half CV squared gradually, causing the charge to vanish. This is an instant of time where the current flowing through the circuit is I, and the capacitance is C. I could apply KVL in the loop at this instant of time, right? The drop from here to here is going to be IR, and then I go this way. The drop from here to here is going to be algebraic charge on the first plate divided by capacitance. See, I'm traversing the loop like this. Algebraic sum of the drops in a closed loop is always 0. So the drop from here to here in the proposed sense is IR. Then I go this way from here to here. Charge on the first plate divided by C would be the algebraic drop. What's the charge on the first plate? Minus Q divided by C. And this must add up to 0. Now, I is what? Magnitude of dq dt. But do you realize Q is decreasing with time? Q is decreasing with time, isn't it? That's how it's getting discharged. This Q is decreasing with time. So dq dt must be negative. And if dq dt is negative, then mod dq dt must be minus dq dt. Mod dq dt must be minus dq dt. Right, Nilesh? Algebraic drop. Algebraic drop. From here to here, the algebraic drop is going to be charge on the first plate divided by C. Now suppose Q is positive. Then from here to here drop will be negative because there is actually an increase, isn't it? From here to here, there is an increase. So the algebraic drop has to be negative, which is what happens. Algebraic drop is negative. Right? So this is the most generalized way of looking. If you do not know the sign of Q, you talk of an algebraic drop. Charge on the first plate divided by C. If you were to travel from here to here, then the algebraic drop would be Q by C. Okay. So let me plug in I as minus dq dt. So I as minus dq dt. Q by C. Q by C. Right? So we have dq by q equals minus dt by rc. Integrate both sides. At t equal to 0, q was q naught. At t equal to t, q became q. This will give me q as a function of time. So this would give me log q by q naught. Is minus t by rc. This gives me q equal to q naught e to power minus t by rc. Right? So at t equal to infinity, q becomes 0. Q decreases exponentially, which is good for the circuit. The circuit would be less vulnerable towards losses, towards damage, physical damage, towards physical damage. The charge time characteristics. At t equal to 0, we had q equal to q naught. At t equal to infinity, q will become 0. Right? That's the discharging characteristics of a capacitor. There are a few nitty-gritties involved here, which I will not discuss right now because I need to tell you Thevenin's theorem and a few other things that will come in our digressions on electrical circuits. Is that fine? Now, have I discussed in the class the force between the plates of a capacitor? No. These are two plates of the capacitor with charge, surface charge density sigma and minus sigma. Sigma and minus sigma. I now want to be able to find, obviously they have charges of opposite signs, so they attract each other, right? And you have to estimate the force of attraction between these two plates, because otherwise when you charge the plates of the capacitor and the plates, eventually they will collapse into each other and the whole purpose of capacitance will get defeated, right? So there would be a mechanical arrangement that would balance this force of attraction and maintain the system in mechanical equilibrium, right? Therefore, it is an important aspect of capacitors to be able to estimate, well, this is a capacitor and I'm going to charge it to a maximum extent of this. Q is the maximum charge, and therefore I must have a mechanical arrangement which will prevent that maximum possible force of attraction for the purpose for which it is designed, right? Now, suppose A is the area of overlap of the two plates. What's the field here? Sigma by epsilon naught is the field here. Sigma by epsilon naught is the field here. Total field, but do you realize that total field, uniform electric field between the two plates of the capacitor is, because of this sigma, this is sigma by 2 epsilon naught. Because of this minus sigma, it is minus sigma by 2 epsilon naught in the opposite direction. Yes or no? Because of this sigma, it's sigma by 2 epsilon naught here. Because of this minus sigma, it's going to be minus sigma by 2 epsilon naught in this direction. That means it's actually minus sigma by 2 epsilon naught in this direction is like sigma by epsilon naught in the sigma by 2 epsilon naught in this direction. So both the plates contribute sigma by 2 epsilon naught and sigma by 2 epsilon naught from the positive to the negative plate of the. Didn't understand this, no? If there is an infinite sheet of charge with surface charge density sigma, what's the field that it produces? Sigma by 2 epsilon naught. This is like an infinite sheet of charge. The field that it's going to produce is going to be sigma by 2 epsilon naught. This is also like an infinite sheet of charge. The field that it produces is minus sigma by 2 epsilon naught in this direction, which is like sigma by 2 epsilon naught in this direction. So the total field, which is sigma by epsilon naught, is constituted equally sigma by 2 epsilon naught and sigma by 2 epsilon naught by the two plates of the capacitor. That is what transpires. Are you there with me on this? Right? Now, if you look at this plate, for example, right? This will experience a force here, but the plate will not experience force because of its own charge. It'll because of its own electric field, right? The charges here will experience force because of the electric field produced by this plate. Yes or no? That means if you look at the top plate, the total charge on the top plate is sigma into A, and the force that this experiences is going to be because of the electric field produced by the other plate. It will not experience a force because of the electric field produced by its own charge. Now the electric field produced by the other plate is sigma by 2 epsilon naught like this. E other so the force that this plate will experience is going to be Q into E other. The force that this experiences is going to be Q into E other. Q is sigma A into E other is sigma by 2 epsilon naught. Right? Which is like sigma squared A by 2 epsilon naught. If you write sigma as Q by A, that's going to become Q squared by 2 epsilon naught A. That's the force of attraction between the two plates. That's the force of attraction between the two plates of the capacitor. So there has to be a mechanical arrangement that will withstand this force and that will keep the two plates in equilibrium, in mechanical equilibrium when they are charged. When they are not charged, there would be no electrostatic force. But when they are charged, this would be to the extent of Q coulombs, then the force of attraction between the two plates is going to be Q squared by 2 epsilon naught A. Yes or no? This is another way of looking at it. We can look at it from energy considerations as well. Do you all understand this? No? Or have I confused you? I'll explain again. Huh? Explain again? No? Anyone? Let me also look at it from energy considerations and compute the force of attraction between the two plates. Right? But this has been registered by all, right? So you know, actually, this is the whole thing is placed in a hub. So if it's a hub, you know, there would be, let's say, mechanical joints that would come here, and these joints will withstand that force. Right? If they want to collapse into each other, there would be tensile forces in these small arrangements, you know, which will prevent them from collapsing into each other. Capacitor ऐसा नहीं कि साला दो तो प्लेट दे दिया तुमको और बोलेगा एक कैपेसिटर है घुसा दे सर्किट में समझ रहा है? There is a full-fledged mechanical arrangement into which it's packaged. Right? कभी कभार क्लास इतना अनपार्लियामेंट्री हो जाता है, रादर पार्लियामेंट्री हो जाता है कि बाहर देने लायक नहीं होता है। सो कुछ भी निकल जाता है, अनप्लान्ड तरीके से बोल देते हैं ना। दिस इज फास्ट ब्रीडर विदाउट अ मॉडरेटर। हाँ। Let me also explain this in an energy domain. You know the force between the plates of the capacitor. Say this, these are two capacitor plates, area of overlap A, and say D is the separation between the two plates. I imagine one plate to be fixed, say. I imagine one plate to be fixed. And let's say I could move the other plate, for example. The force between the two plates is F, and let's say the two plates are charged with Q and minus Q respectively, one at the expense of the other. What is the potential energy of this? If C is the capacitance, the potential energy initially of this is what? Q squared by 2C. C is what? Epsilon naught A by D. That's the potential energy of this. Now, if I want to pull this plate apart without adding kinetic energy to this, then I must just about be able to apply an external force, which is F upwards, just about exert an external force F upwards, so that I could move this upper plate, right? Yes or no? Slightly more than F in reality, but for all practical purposes almost equal to F, so that I could pull this plate up opposing this force F, right? So this is force exerted by an external agent, force exerted by an external agent, and this force exerted by an external agent, let's say, causes the separation between the two plates to become d plus dx when I apply this force F. However, what happens to the charge when I pull the plates apart? What will happen to the charge? वही रहेगा, जाने का इसके पास रास्ता कहाँ है? Until and unless I had a battery connected, which in response to change of capacitance will cause charge to flow, maintaining the potential difference constant. Until then, the charge, if these two plates are isolated and not connected to each other through a battery, the charge will remain preserved. The charge will not change. What is this capacitance? New capacitance? Q squared by 2C. What's the new capacitance? C is epsilon naught A divided by D plus dx. That's the new potential energy. Yes or no? On applying a force F, let's say the separation increases by an amount dx, then Q squared by 2C. C becomes epsilon naught A by the new separation D plus dx. Yes or no? That's a new potential energy, right? This was the original potential energy. Now, if this force F caused this plate to get displaced by an amount dx, what's the work done by this force? F into dx is the work done by this force. F into dx is the work done by this force, external force, and work done by an external force will go towards two things. One, change of potential energy. Two, change of kinetic energy. But there is no change of kinetic energy. That means this entire work done should have contributed towards change of potential energy. This must have been UF minus UI. And UF minus UI, as you can see, is Q squared by 2 epsilon naught A into dx. Yes or no? So the force of attraction becomes, this dx will get cancelled. The force of attraction, which is also the external force applied, is Q squared by 2 epsilon naught A. Yes or no? Got me? That's the energy way of looking at things. अप्रिसिएशन ही नहीं है तुम लोगों को किसी आदमी का आजकल। हाँ, দেখ তুই এত ভালো ভালো কথা বলিস না, সবার মন খুশি হয়ে যায়। छोड़ ना यार, भालो बोला इतना ही जानना जरूरी नहीं है क्या? और क्या कथा हुआ उसको से तुमको क्या मतलब है? जजमेंटल हो जाओगे फिर तुम।